Okay, so yeah, the goal for today is just to have a really short and sweet lesson on functions. Then I will assign some work for you. We're gonna hold off on the physical textbook that I gave you. We're gonna start off using some digital scans of a different textbook that I prefer, which is this one here. So I didn't think it would be a good idea to give you two full textbooks. So you have the physical one here, which is the concepts and calculators. And then occasionally I'll sort of scan a page from this one. This is Stewart's Calculus. So we'll kind of go back and forth between these two books. Our main guide, though, will be this book. We'll kind of be following along. This book goes very closely, like, and if you're not here, I'm talking about the calculus concepts and calculators, the physical book that everybody has. This book goes really like closely hand in hand with the AP Calculus curriculum. So almost chapter for chapter is like the different units of the AP curriculum. So this is kind of going to be our guide. Also, this book has a lot of interesting stuff with respect to calculators. So in this class, we will be using these graphing calculators a fair bit. I highly recommend that you get one if for some reason you cannot obtain one of these calculators. I do have some extras. We're not going to need one today. So if you want to take it out, you can. There's nothing wrong with that, but you definitely don't need one today. If you do need help sourcing one, I can lend you one of mine. The school has a few, and I have a couple of personal calculators that I can lend you, but that is a lend, so you do have to give it back at the end of the year, because these aren't cheap. I think that even the sort of the older style, the TI-83, which, if you can believe it, came out sometime in the 90s, so before you guys were even born. I don't know why they're so expensive. I mean, you know, most like little watches have more technology than one of these now. But I guess it's just about copyright and that kind of thing, and intellectual property. So I think that even these ones are about $80. And then there's the nicer ones as well. The TI-84, or if you're fancy, the TI-84 Plus. So these are I think around $120. So they're not cheap. And then if you're super fancy, then you might have one of those N-Spire ones. Those ones also work. They're definitely not necessary, but they're very nice. I think they have like a backlit screen with high definition and stuff, and I think those are around $200 or thereabouts. So if you do need to borrow one, that's completely fine. You'll have to borrow one of mine, but you have to give it back at the end of the year. So anyways, what I was saying is that this calculus, the hard book that we actually have, has a lot of good stuff on writing your own calculator programs. So the cool thing about these calculators is not just that they've got a nice big screen, and not just that they can make a graph, so you can graph things on here, which is really cool, but also you can write your own computer program and actually save the program. So that's why these are often referred to as programmable calculators, because you can write a little computer program and have it saved in here. And we will be using some of those computer programs throughout the year. And that's what's so great about this book, is that they actually kind of walk you through step by step how to write your own computer program on here. So if you're not super into programming, you don't have to worry. You can just copy letter for letter. Like, they give you the full instructions on how to do that in this book, and then you have it saved, and you are allowed to use that on certain tests. But for the most part, you don't really have to use that for tests. It's mostly just to develop your understanding. Another quick announcement too before we jump in. And if you're watching the YouTube video, I know this is a little bit boring without any visuals. You're just listening to me talk, but this course does have a syllabus, which is like a course outline to kind of tells you what the expectations for this course are. I am still in the midst of writing it. So this is the first time I've had to write one. I did just submit the like last year's syllabus, but I guess since certain things have changed, that was rejected. So I'm actually writing my own now, and it's already several pages long. They've got a lot of requirements of what goes on that syllabus. So if you're wondering why, like maybe some of your classes you already got a course outline, you're still waiting for mine, I apologize. I spent a good portion of my weekend writing it, but I should show you some of the expectations for the syllabus. It's I think like a maybe 13-page document that just tells you the things that need to be on the syllabus. So it's quite intense. They need certain examples of like some of the activities that we're going to do, some of the types of questions we'll be answering and stuff like that. So it's very detailed. Usually my course outlines are like, yes, this class we will be doing quadratics and rational functions and this and that, and then this is my email address, this is the room number, and done, right? That's what most, course outlines look like. But because this is for the College Board, it does have to meet certain requirements. So please stay tuned for that. I'm hoping to be done by the end of the week. I'm pretty sure it should be done. I mean, hopefully by the end of the day. I've scheduled some time today to write it. Anyways, expect that soon. All right. Okay, so last class, we looked a little bit at here it is. Let me just quickly erase this. I don't know why that's there. We looked a little bit at this little sort of brain twister, right? And we looked at the different types of functions that this could be. Okay, and then we were asked what's different about these two topics. Did anyone come up with any sort of interesting ideas about the differences and similarities between these two functions that they'd like to bring up? Okay, let's take a look at the graphs of these two functions. Let's just kind of jump right into this. So I think I've mentioned a few times before, I really like using Desmos for graphing things. So I'm going to sort of pop Desmos in over here. You should be able to see both at the same time. There we go. Okay, so let's try this one. I've got y equals sine of 2x. Okay. Now, does anyone sort of recognize that shape? Yeah, I'm seeing some heads nod. Can anyone tell me what that shape is called? What do we call this shape?
Is it a sinusoidal?
Yeah, it's a sinusoid. Yeah. So if just in terms of like the way the word works, sinusoid is the shape. That's the general shape, like a square or a circle or a sinusoid. And then sinusoidal is saying like that shape looks kind of like a sinusoid. So it's sinusoidal is adjective, sinusoid is the noun. Okay. Yeah. So this is a sinusoid. This is like looks a lot like a sine wave, right? Is it different than a sine wave? Like if I were to graph y equals sine of x, would this look any different or would it be about the same?
Sine of y. No.
You think you might be thinking of cosine?
Oh, not cosine.
Yeah, cosine starts at the top. Yeah.
All right.
Yep. So this is sine is equal to, or sorry, y equals sine of 2 times x. What do you think would happen if I wrote y equals sine of x? Would it be like more narrow or would it be more stretched out? What do we think? Or would it be the same? Okay, so we think maybe a little more narrow. Okay, let's just punch it in and see what we get. Okay, so looks to me it's actually a little more stretched out, right? So that when I multiply that by 2, when I multiply we call this the argument, the x in there, the thing that's in the brackets. When we multiply that argument by 2, that has a tendency to compress it. Okay, so the larger our value is, the faster that goes. Okay, so we'll talk a little more about trigonometry as the course progresses. I do get the sense that trig is kind of one of the topics that we struggled with last year, just by looking at some of the results from the diagnostic test that I gave you last week. So I think we will have to maybe spend a little bit of extra time reviewing trigonometry and how that works. But in general, we can kind of see that as the argument, as the thing inside in the middle gets bigger, what that corresponds to is a higher compression. Okay, so things are getting compressed. So we had one of these was y equals sine of 2x. That's what we have here in red. The other one was sine of x squared. Okay, so what do we think that is going to look like if we were to graph this? How do you think that's going to look? Yeah. Everything's going to be positive. Okay, and why is that?
It doesn't matter if the x is positive or negative. The square is positive or negative.
Okay. So we've got some stuff about positives here. So I know that no matter what, if x is less than 0, right? If x is negative, then x squared, it's still going to be greater than or equal to 0, right? And I'll put a little equal sign here too. So if x is less than or equal to 0, then x squared is still going to be positive, or at least 0, right? Now, so does that mean, so if x is greater than 0, does that mean that sine of x is greater than 0? So if I have a positive value and I take the sine of that positive value, will I still get a positive value back? Let's take a look at our original sine graph here. Okay. So anything past this 0 here, anything past the origin, this corresponds to positive x values, right? Okay. And it looks as though I'm still going to get some negative y values back, even though I've got positive values. So I like your observation that x squared is still going to be negative, or sorry, it's always going to be positive. But we also have to remember that we can still get negative values out of sine, even if the number that we're plugging in is positive. Okay. Okay, let's have a look at and see what this graph looks like. Let's try y equals sine of x squared. I'm going to hide this one. Okay. So let's have a look at what's going on here. Let's see if we can try to figure out what's going on. And what I'm going to do, just so that we can sort of get a little more resolution, I'm going to just stretch the y-axis so we can kind of see what's going on, and then I'm going to do that. Okay, so this is not to scale anymore. Okay, so just take note of the values that we have here. So this is the value 1, and this is also the value 1. So each of these squares does not actually represent a square, right? So it's more like this rectangle here is a rectangle of 1 by 1. Okay, so we have some symmetry. It looks like we got some symmetry, and let's see what happens as we move away from the origin. Do we notice anything happening here? Hey. Now, this is all just like a block almost, right? So it's hard to even see what's going on here, right? It's all just going back and forth so quickly that there aren't even enough pixels on the screen to represent the differences, right? But as we get closer and closer to 0, it starts to look more and more like a regular sine wave. So let's go back and show our original sine wave. Okay. It looks like these two functions have almost nothing in common, right? Like they're very different. They're very different. Okay. So what I'd like you to do just this evening, I'd like you to think about where does this sine of x squared, how is that even remotely related to the original sine function? Because it looks completely different, doesn't it? It looks completely different. So let's go back here. So I'd like to talk a little bit about functions. We're going to develop a little bit of vocabulary. I'm hoping it's vocabulary that we're somewhat familiar with, and then I'm going to assign you a few questions to work on, just so that we make sure that we're doing okay. So let me scroll down a little bit. Okay, so let's talk a little bit about what a function is. Okay, so a function here, this is a definition of a function. So a function is a rule. It is a rule that assigns to each element x in a set D exactly one element called f of x in a set E. Okay, so a lot of words here. So it's a rule. It's a rule that assigns to each element x in a set D exactly one element called f of x in a set E. Okay? Okay, so what do you think we mean by the word rule? What do we mean by rule? Do we have any rules at Grant Park right now this year? Okay. Would you say that everybody has to follow the same rules? Okay. Yes. It's kind of like a set of instructions that everybody has to follow. Right? Even if you are different than somebody else and you have different needs and you're a different person, you still have to follow those same rules. So just like in real life, a rule is just something that you, like a set of instructions that you tell a number to follow, or maybe not even a number, and every single number or whatever you're dealing with in your set D has to follow that rule. Okay. So a couple of words here. So I've got set. Okay. So we've used the word set here. I want to just quickly define what the word set means. So a set is a collection of objects. Collection of objects. Oftentimes we use numbers in sets. Okay. So a set could look something like this. So we might have a set A. A would be a perfectly valid set. And we would use curly brackets. Okay. And A, B, C, maybe 1, 2, 3. So this would be an example of a set. Those would be all of the objects that we collected in our set. Okay. We also have the word element. An element is just something that's in a set. Okay, so when we want to refer to the objects in a set, we refer to them as elements. Okay. So for example, we would say that A is an element of the set A. Or in other words, A is an element of the set capital A. Okay? So those are the words that I think we might really need to have under our belt to understand this definition of a function. But the idea of a function is that we're taking elements in a set D. The set D we call our domain. Okay, and E is where we're taking those elements. And E is called, well, often we'll refer to E as the range. But the more accurate definition would be the codomain. Okay, so it really sort of depends on how you're defining your function. But we'll talk more about the difference between a range and a codomain shortly. So we're taking elements in our domain and we're assigning them exactly one value in our codomain. Okay, and there's several different ways of describing how a function like this works. Okay. So I've gone ahead and I found a few different images that can kind of help us describe a model of a function. So this right here, this would be a machine model. So this is called a machine model. Okay. So the idea here is that we take an x. X is kind of thought of as our input. Okay, and we input our function or our element x into our function, and out comes our output. Okay, so that's kind of the initial way we think about a function as an input and an output. So you can kind of think of like it as a computer program, right? You input some value, and then the function would output a different value. Okay, so all of the numbers on the left here, this would be from our domain. Okay, and it's going to output some number in our codomain. Okay. This here is perhaps my favorite way of describing functions is with a mapping. So this is a mapping model. Okay. So the idea here is that on the left here, this is our domain. So these are all of the possible values that our function can take. Okay. And then the function is thought of as the arrow here. So the function is taking values in our domain and mapping them to elements in our codomain. Okay. So it's going to take this value x and it'll bring it to f of x. It's going to take a value a and map it to f of a. So we're applying the function to these different values and we're getting a value in our codomain. Okay, so that's our mapping model. This is probably the most familiar model that we use to describe functions, which is a graph. Okay, so there's many different ways of graphing functions. This particular type of graph is called a Cartesian plane. Okay, one of the topics that we will cover is a different way of graphing functions using what's called polar coordinates, kind of like a polar bear. Okay, so that's, I think, maybe the last chapter in our book. So we'll kind of put that on hold until, let's say, April. But in April, we will talk about different ways of graphing functions that look completely different, even though it's a very similar method. You're still graphing functions. So I think that this is the one that we're most familiar with, right? You have your domain, which is your x values here, and then each value in your domain gets mapped to a single value in the codomain. Okay, and all of the values in your codomain, we call that the range, right? So the range is all of the y values that you used. Okay, the codomain, I keep using that word codomain. The codomain refers to your whole set of y's, like all the different possible outcomes that you could have. But your range is the values that you actually used. Okay, so codomain is just everything. Your range is the set of values that you actually use in your function. Okay. And then finally, we have something called a table. Okay, so this is a perfectly valid method of describing a function. So of course, the left here would be your domain, and the right would be your codomain, okay? Or in this case, because it's just listing all the values that we have, this would also be your range. All right, so there's a few things that we should know as well. So we may have heard of the vertical line test. Vertical line test. Is this something that you guys are familiar with? Or you've seen the vertical line test before? Okay, so when we graph a function, if we can manage to draw a vertical line at any point, and it only passes through those vertical lines at a single point each time, that means that the graph that we've drawn is a function, okay? Because that's saying that each one of these x's goes to a single value y in the codomain, right? Which satisfies our definition of a function. But you can see here, now that we've sort of gone back and looped around, this curve does not represent a function because if we draw a vertical line through here, then at this point A is being mapped to two different values, okay? So another way of sort of representing a function and making sure that it is a function is using the mapping model. So if I were to have, several points here like this, like maybe I'm taking my function from set 1, 2, 3, and the codomain is a set A, B, C, okay? So a function should take every single value in the domain and bring it to one value in the codomain. But if for some reason I had, okay, so let's say that we have this really straightforward relation, but then in addition to, say, 3 going to C, I also had that 3 goes to A. Now, this causes me to have a problem. So this is our problem. Okay, our problem is that 3 maps to both A and C. Okay, so that would be a problem. So that would not be a function anymore. So yeah, in the interest of just keeping this lesson really short and sweet, I'm going to end it there. So we just have a really straightforward idea of what a function is, and just a recollection of the vertical line test, so that when you look at a graph, immediately you can determine whether or not that graph represents a function. So I'm gonna post some questions on Classroom in about 2 minutes time. So stay tuned for that. And they'll just be straightforward questions about functions, just so that we can sort of recall any of those major facts that we may have learned in grade 12. Okay. Are there any questions about this? Yeah, this isn't intended to be super challenging. So yeah, I'm hoping that hopefully by the end of the week, we can kind of get into some more meaty problems. But for the time being, yeah, we're just going to sort of take a look at what functions are and kind of remind ourselves of some of the terminology. Okay. And that video there.